Welcome to Calculus. Today we will investigate finding derivatives of functions using the definition, focusing on the algebraic limiting process to arrive at numerical derivative values. We'll take a look at three examples, three different types of functions. The first is linear, the second is quadratic, and the third is rational. Let's take a look at this first example where we find the derivative of a linear function. So our function given is y equals 2x plus 3, and we're interested in taking the derivative of that linear function at the x value of 1. So we need to remember our definition of a derivative in order to complete this task. So let's write that out first. So again, let's just write derivative. And we've seen this definition before in the context of the slope of a tangent line to a graph at a given point. So the derivative really is a version of our average rate of change fraction, but we are taking the limit. So it's the limit as x approaches c of this fraction f of x minus f of c over x minus c. And you can see in that fraction arrangement, it really is a version of that simple rise over run, the change in the y over the change in the x, really the slope. Well, let's apply it to this particular linear function, y equals 2x plus 3. So I just want to define quickly what's my f of x, my f of c, my x, and my c. F of x is going to be the function itself. So what I'm going to call f of x is 2x plus 3. And x is going to be x. That's the one thing we do not change in the rule. I do want to also define f at c and c. So I'll start with c itself. C is this value 1. So it's an x value that we're actually considering as a number. F at c then is equivalent to f at 1. So to calculate that, we want to just substitute in this value of 1 for x. So it's 2 times parentheses 1 plus 3, and then I want to evaluate. I'm going to use that as a numerical number. So that's 2 times 1, or 2 plus 3 is 5. So f at c has the value of 5. So we've got our four pieces laid out. I just need to substitute them into the derivative definition. So the way we'll calculate it is going to be the limit as x, my c value is 1, as x approaches 1 of the function. So we'll try to color code here, 2x plus 3 minus f at c, again that's the value of 5, all over x. So again, x is x. The one thing here that we don't substitute out a different value for, minus our c value is 1. So there we see how we use the derivative definition in conjunction with a function and a specific x value to fill in here. So at this point it's set up, and I want to now simplify that limit of the average rate of change, or the slope of a tangent line. Let's work on that numerator first. So I'm going to simplify that really by taking away the parentheses. And at that point, what I see is that I've got 2x plus 3 minus 5. So I can add the constants there. It's going to be 2x plus, really, minus 2. And that's all over x minus 1. So my next step, I'm looking for a cancellation. We could try direct substitution, but remember, the way we've created this version of the difference quotient, it's going to be an indeterminate form, 0 over 0. So I won't try direct substitution yet. I'm going to look for a cancellation that I can create in the numerator and in the denominator. So I see in my numerator 2x minus 2, I have a common constant value in the coefficients of 2. When I factor that out, I'm left with x minus 1. And that reveals the cancellation. So I'm ready to cancel above and below that common binomial x minus 1. And there's not a whole lot of calculations left. At this point, I have the limit as x approaches 1 of simply 2. So you can recall when we're thinking in terms of limits, this 2 represents a function. So if I were to graph 2 on the coordinate plane, it would be just a perfectly horizontal line going through y equals 2. And so if I think about what's the y value as x approaches 1, it's the same as the y value everywhere on that function. It's a constant 2 across the board. So there's no calculations to complete there. The limit is 2. Now, if we think about geometrically what that's asking about the original function, if I were to just sketch that original function, 2x plus 3 has a y-intercept of 3, slope of 2. And if we think what's the slope of the tangent line at 1, we'll recall that a linear function has a constant slope across its whole domain, which is going to be 2. The slope of the tangent line has to be actually the line itself. And we can see that in the mx plus b form. So it turns out we probably could have gotten the answer 2 just by looking at the equation and interpreting it geometrically. But we are after finding the derivative using the definition. So that all supports each other. The algebra supports the geometry there. Let's take a look at a second example that's quadratic. Our task is again presented to us the same. I want to find the derivative of the function at the given value using the definition of the derivative. Let's write that again. The derivative, the way we're defining it currently is the limit as x approaches c of f of x minus f at c over x minus c. Same thing, same rule that we've been using. So over on the left, again, the way I want to start is by defining what's my f of x, what's my f of c, what's my x, what's my c. F of x is just negative x squared plus x plus 1. It's our function. And we want to find f at c. Well, first let's write x itself is just x. C is given to us in this value here. So we're interested in the slope of this quadratic that opens downward at the x value of -1. So our c value is -1, which means when I calculate f at c, it's going to really be f at -1. And that I actually want to run through the function, the quadratic. So it's negative parentheses -1 squared plus -1 plus 1. We want to simplify that out. So I'm going to start here with the squared -1. -1 times itself is +1, but there's a lurking negative out there, which it takes that value. So -1 plus -1 is -2 plus 1 is -1. So f at c has a value of -1. So let's set up our derivative. So the derivative of this function is going to be the limit as x approaches that c value of -1. In my numerator, I'm going to write the function. So that's the actual one in blue here, negative x squared plus x plus 1 minus, and then f at c we determined to be -1. And that's all over x minus and then the c value itself is -1. So no surprises with the setup. Again, I'm using those same principles of writing out that difference quotient, the average rate of change fraction, and then defining f of x, f at c, x and c, and just substituting them in. Now I need to simplify that expression, that limit expression. So the first thing I need to do is decide on the numerator. So the double negative here on the c value is going to cancel and become positive. So my next step is going to look like that this is the limit as x approaches -1 for the function -x squared plus x, and then 1 plus 1 is going to be +2. Same type cancellation of a double negative in the denominator. X minus -1 is x plus 1. And then I need to, again, find some kind of cancellation in terms of a factor above and below that will cancel. Since currently, if I did direct substitution, I would get indeterminate form 0 over 0. So what I'll do with that numerator is I want to factor out a negative sign to give my quadratic x squared term positive sign, because currently it's -x squared. So I'm going to factor out a negative. That gives me x squared minus x. Notice it switches all the signs on the trinomial, -2. And then I'll just bring that denominator. I want to factor that quadratic in the parentheses. So what I'm looking for is what multiplies to -2 and at the same time adds to -1. What multiplies to -2 and at the same time adds up to -1. And again, we're getting those from the c term and the b term on that quadratic, ax squared plus bx plus c. And it looks like those values for us are going to be -2 times +1. -2 times +1 is -2. -2 plus 1 is -1. So that's a good way to factor. So this becomes x minus 2 times x plus 1 over x plus 1. And that factorization reveals the cancellation. And that is going to be this common binomial x plus 1. Now we're ready to see what's left and then apply direct substitution to find the limit value, which again is going to be the slope of the tangent line to this quadratic at x equals -1. My denominator has canceled, so it's now -1 times x minus 2. So no problems here with direct substitution. I'm going to plug in that -1 for x from the limit. And the inside of that fraction, or that parentheses, -1 minus 2 will be -3 times -1 is +3. Again, we should interpret this geometrically. If I look at this function, it's a downward opening parabola because it's got that negative on the x squared, has two zeros. One's at 2, the other's at -1. So it has some shape, and we're just roughly sketching it in here, like so. And so what we're saying is that at the function at -1, and that's right where we've got that 0, the slope of the tangent line, let me sketch that so it only intersects once, should be 3. The slope of the tangent line equals 3, because remember, the geometric interpretation of the derivative is what's the slope of the tangent line at the point, in this case, -1, 0 on the graph of that quadratic. So we've taken a look at an example that's a linear function, finding its derivative according to the definition. We've also done so with a quadratic function. Let's round it out by taking a look at a rational function. So here I've got 1 over x plus 3. That's my f at x. So we'll start defining now that we've got the hang of the task. So the f of x is 1 over x plus 3. Remember, x will just be x. My c value is given as -2, and f at c I want to calculate as f at -2. So plugging in -2 to my function is 1 over -2 plus 3, which is 1 over -2 plus 3 is 1. That's 1. So f at c has the value of +1 there. Let's write our derivative definition again. Is the limit as x approaches that c value of the difference in the y value, so f at x minus f at c, all over x minus c. Now we're ready to substitute in our 4 found values into our expression. We want to calculate the limit as x approaches that c value of -2 of the function 1 over x plus 3 minus f at c, which is given to us when we substitute -2 through the function as 1. And that's over x, which is x, minus our c value, which we've already decided that's -2. Again, what we've done is we've defined our f at x, our f at c, and our c, and then we've substituted those values into the derivative definition. Now we're ready to simplify. And really what we want to do at this time is combine the fractions in my numerator. So I'm going to consider that this is 1 over 1. So I want to make those two fractions one fraction. So just taking a look, I see that my common denominator is going to be simply x plus 3. So I want to take the limit as x approaches -2. Won't change the first fraction, 1 over x plus 3, but I will change the second one to be x plus 3 over x plus 3. You can tell that that has the value of 1. It's something divided by itself. But now they have the same common denominator. Denominator of the whole complex fraction is x minus -2 becomes +2. So the name of the game at this time is simplify the fractions. That said, I'm going to combine my numerator fractions into one complete fraction now. So in my numerator, I'm going to have 1 minus parentheses x plus 3 over the common denominator of x plus 3 over x plus 2. Now I can combine my numerator of the numerator. So this is the limit as x approaches -2. 1 minus x minus 3 becomes 1 minus x minus 3 because I distribute that negative to each term. So that numerator is going to become -x minus 2 over x plus 3 over x plus 2. So again, at that point, I'm looking for a cancellation. I am faced with this situation where direct substitution would give me the 0 over 0 indeterminate form. So I'm looking to cancel some stuff out. And I see I've got very similar binomials. The only change between the two is the sign. So I want to factor this numerator of the numerator, factor it out a -1. So that next step is going to be the limit as x approaches -2 of -1 factored out. What that will leave is two positive signs, so x plus 2 over x plus 3 over x plus 2. And then at that point, I'm ready to collapse that complex fraction into a simple fraction. And one way to do that is to multiply by the common factor 1 over x plus 2 above and below. So definitely algebraically that's legit because it's got the value of 1. Something divided by itself equals 1. So in the denominator that cancels my x plus 2. In the numerator it cancels this x plus 2, and all those cancellations really help us out in terms of finding the limit value, because now it's limit as x approaches -2 of the only thing left, -1 times 1 is -1 over x plus 3. Everything else is canceled away. Now we're ready for direct substitution. So this is now -1 over, instead of x, I'm going to plug in -2 plus 3. And that will reduce to -1 over -2 plus 3 is 1, -1. Again, what we should decide is geometrically, what is that describing in terms of the original function? So if we were to sketch that f of x is 1 over x plus 3, that is a rational function with a vertical asymptote going through -3. It's got a horizontal asymptote at the x-axis. And it would have this arrangement, the leftmost branch would be down here in quadrant 3. The right branch would be in quadrant 2 and then turn sharply into quadrant 1. And again, what we're saying is that what we're calculating is at -2, the slope of the tangent line at that x value is -1. And that geometrically has the appearance of a line with a slope of -1, which again supports the algebraic strategy here with the limiting process. Well, thank you for joining for this investigation of finding derivatives according to the definition at specific x values. Thank you for joining. I'll let you go work on your problems. Look forward to seeing you soon. Bye for now.